And so most of the time people read the CV and tell where they graduated and some of their honors and things like that. But with Greg, it's kind of a unique person. And so I wanted to talk a little bit about one aspect of Greg that not a lot of people know. Those of us who are Facebook friends with him always look forward to his haikus. And so Greg manages to post almost entirely in haiku various observations about life, his daily experiences, things like that. And even when he writes a paper, he will sometimes give a description of the paper as a haiku. And so I got to know Greg at the IPCC last assessment when we worked on the same chapter together. And after the IPCC, Greg did something amazingly cool. He painted a whole series of watercolors and wrote a series of haikus and published it as a little book that describes the IPCC results in a very nice fashion. And he published it on his own dime and distributed it to people. Hopefully you've saved a few for the new administration that you can send out. But that's not the coolest haiku thing that Greg has done. He has managed on his last paper that he published.
Second to last now.
Second to last. Okay, I haven't seen the last one yet. He used a haiku as the title. So it's not hidden in the acknowledgments, it is the title. So here it is. Maybe I should have you read it.
Okay, I'll read it.
Because you can do it better.
Yep. And it'll be in this talk, actually. As El Nino builds, Pacific warm pool expands, ocean gains more heat. And that is...
So I think if we could all aspire to use haikus as the titles of our papers, it would be much more readable. So anyway, with that, I give you Greg.
All right. Good afternoon. Thanks, everybody, for coming. It's great to be here. I would like to talk today about improving estimates of Earth's energy imbalance. This is work that I've done with John Lyman, who works with me at NOAA's Pacific Marine Environmental Lab, also with Norman Loeb, who works on CERES top of the atmosphere energy imbalance estimates at NASA, and also Abby Birnbaum, who was a NOAA Hauling Scholar summer intern last summer and is a co-author on that haiku titled paper. So this is going to be sort of a three-part talk. The first part is really an introduction to global energy flows and why you might want to look at the energy imbalance through energy storage estimates, that is through ocean warming. The second part will look at interannual variability in terms of the Earth's energy imbalance and its relationship to El Nino, and that'll use both in situ data from the Argo array of robotic profiling floats and satellite data at the top of the atmosphere from CERES. And then we'll talk about the next biggest term in the Earth's energy imbalance, and that's the global half the global ocean that's below the sampling depth of Argo. So, global energy flows and thermal energy storage, introduction. We'll talk about ocean warming estimates, instrumental and spatial sampling improvements over decades, and finally finish up with Argo estimates of ocean warming for the first part of the talk. All right, so this is from the Intergovernmental Panel on Climate Change's fifth assessment report from Working Group 1, which reports on an assessment of the physical science basis for climate change. And what this shows, it's a complicated schematic, but I'd actually just like you to focus on the bottom and the top of it. So the top of it shows an incoming solar radiation of 340 watts per meter squared. And whenever I say watts per meter squared in this talk, it'll be referred to the global average applied over the entire surface area of the Earth, which is what this number is here. And then about 100 of that is reflected both off clouds and off reflective parts of the Earth's surface, say deserts or ice caps. And then 239 watts per meter squared goes out as long wave radiation. So the Earth, is warmed up as a result of the sun heating it and re-radiates this back out to space as long wave. So we've got incoming short wave, reflective short wave, and outgoing long wave. If you do the subtraction here, you'll notice that these don't add up, and that's Earth's energy imbalance, okay? And it's about a watt per meter squared. There's all this complicated stuff in between, but in the end, you have an imbalance of about 0.6 of a watt per meter squared. And chapter 2, the atmospheric chapter, put this at modern times as somewhere between 0.2 watts per meter squared and 1 watt per meter squared. It has a fairly large uncertainty. So this is an imbalance of 0.6 of a watt per square meter. I like to give the atmospheric scientists a little bit of a hard time because they put it into cornfields. It doesn't go into cornfields, it goes into the ocean, all right? But all joking aside, this is a small difference of big numbers, and so maybe that's something that your physics 101 professor tells you is a difficult thing to do. So maybe it's better to try to look at this in terms of storage change, and that's what was done in the chapter that Don and I were lead authors on. The Oceans Observations chapter, where we did an assessment of the thermal energy storage in the climate system from various published estimates in the literature. So what this shows is from 1970 through about 2011, it shows the cumulative energy storage in various parts of Earth's climate system. And this is in zettajoules, 10 to the 21st joule. So each one of these has 21 zeros after it. What you see in this light blue area here is the amount going into the upper ocean, and here upper ocean means the top 700 meters of the ocean, and I'll tell you why in a little bit. It's basically instrumentally motivated. Deep XBTs go to 700 meters, maybe a little deeper, and so there's quite a bit of XBT data in the early part of the record, so that's why we cut it off at 700 meters. The deeper ocean, below 700 meters, is in dark blue. The amount of energy that goes into melting ice, both sea ice and glaciers and ice caps and ice sheets in Antarctica and Greenland, is this whitish color. This mustardy color here is actually lithospheric warming, land warming, and that's a long-term estimate from departures in borehole temperature from what you might expect. And then the tiny little sliver here is the part that we live in, the atmosphere, and that's both warming and moistening. And it's about 1% of the entire budget. The ocean is about 93%, and ice melt and land is about 3% each. Now the long-term estimate here is about 0.4 of a watt per meter from 1971 to 2010. If you go from 1993 to 2010, it's 0.5 of a watt per meter squared. And I've forgotten what exactly time period the atmospheric chapter was considering it, but I think it's even more recent. So this number, you can see a little bit of a hint of acceleration there, although I'd be hesitant to fit anything other than a line in this instance. The other thing I'd like you to note here is that there are uncertainty error bars here, and they expand as you go back in time, and that's because sparser observations make uncertainties larger in time. And most of the uncertainty here is in the upper 700 meters of the ocean. That's where most of the heat is going, especially early on in the record. Okay, so if we zoom in on the 0 to 700 meter ocean heat content changes, again, now we're going back to 1950 and through 2010. Again, the axis is zettajoules here. These are the 5 estimates that were assessed in the IPCC report. They all show a trend, at least over the last 4 or 5 decades. As you go back in time, there's a lot of variability, and at least this is my favorite estimate for the uncertainty is from Dominguez et al. It tries to fit EOFs to patterns of sea level, actually, which is related to ocean heat content. But the nice thing about it is that the uncertainties take into account the sparseness of the data, and so you can see them getting quite large as you go earlier than, say, about 1970 or so, and you can see these estimates spread out. There's also some differences among the estimates in interannual variations, and that is because of a whole bunch of different assumptions and methodologies that go into these. These different groups all do different quality control in the data. They have different procedures for quality control. A lot of the data in the earlier estimate is from expendable bathythermographs and mechanical bathythermographs. These are fairly low accuracy measurements that were not really built for climate. They were built for, in the case of the XBT, for anti-submarine warfare. And so they have biases both in the temperature that they measure, and they infer depth from time and a fall rate equation, and that actually has time-dependent biases. The baseline climatology when you're mapping something sparse is important, and the mapping methods that you use are all important. So all those account for some of this structural error, let's call it, in the estimates. All right, so that's really exciting. But here's a picture of the mechanical bathythermograph. Those started really in the 1938 into widespread use. Supposedly an uncertainty of plus or minus 1/10 of a degree C and 1% in depth. In practice, probably a little larger than that. Same with the expendable bathythermograph, which came into widespread use around 1966-67. Again, 1/10 of a degree C, plus or minus 2% depth. And this is a very shallow measurement, less than 300 meters, usually actually around 100 meters depth. There were two models in wide use, one that got to 400 meters and more recently 750 meters. The more accurate measurements are actually down at the bottom. The reversing thermometer here, introduced about 1900. The deep versions of these could get, which had a small range, could be read to, and if people treated them like their kids, actually, they would track the calibrations over the years, but they were accurate to within about 10 milledegrees, and could determine depth to about 1%. More recently, CTDs, which were started in 1961, weren't too accurate initially, but by the mid-1980s, when the World Ocean Circulation Experiment was sort of ramping up, they were good to about 2 milledegrees and about 0.05% in depth, and could get to 6,000 meters. Argo, more recently, since about 2000, has gotten us to about 2,000 meters depth with an accuracy of at least 0.01 degrees C. Actually, we've recovered a lot of these, not a lot, but some of these Argo instruments and post-calibrated them, and the post-calibrations are good to within a couple milledegrees. So they're actually probably better than this, at least for temperature, and they're pretty good for depth too, so 0.1%. So we've gotten sort of increasingly, we have sort of a mix of observations. And this is just an example to show you what this XBT fall rate correction error can do to a heat content estimate. So this is from Johnson Wafel's 2001, and what it shows you is a Dominguez et al. Estimate, which is in brown here. So you saw that updated a little bit through, I think, 2010 for the IPCC. But this is one of the early estimates that actually recognized that there was an XBT fall rate error. And they corrected it by comparing it to a reference data set, the bottles and the CTDs, which are higher accuracy. And when they did that, they got rid of this bump in the 1980s, which was in the original Levitas and Ishii estimates, which was actually used in the IPCC fourth assessment report. And it was one of the big puzzles in the fourth assessment report was what caused this decadal variability in ocean heat content. Well, it turns out it was actually an XBT bias error. Okay, but there were a lot of comparisons to models, and so it was a topic of some investigation, actually, after the fourth assessment report. But by the time the fifth assessment report rolled around, some of this XBT bias errors had been removed. People are continuing to work on this, but it gives you a feel that these are significant corrections, and they're not. It doesn't entirely. Because there are bias corrections out there, they don't actually entirely take care of the error. So this is another way of looking. This is actually a way of looking at the relative proportions of these data in the data set. This is cast per year in thousands, and it shows that early on there was a lot of MBT data in the upper 100 meters, supplemented by bottle data, which were much higher quality and could go as deep as full depth, and then. Starting in the 70s, but certainly into the 90s, the CTD data became more prevalent eventually than the bottle data. You can see these two curves sort of swapping around the World Ocean Circulation Experiment. And then we have this large ramp up of first shallow XBTs, now confusingly in dark blue instead of light blue, but these are actually the upper 700 meters. upper 400 meters measured in this one, and then ramping up and switching over to the XBTs, the deep XBTs, going down to 700 meters. And then you can see the profiling floats ramping up in red at the end of this. And by now, we've gotten a lot further with the floats. So that's sort of a count way of doing it. But what does it actually, what does this look like in terms of like layers and coverage of the global Earth? So this is from a paper that I wrote with John Lyman in 2014. And what this shows, one way of mapping these data, you can just average them in grid cells or something, but if you do an objective mapping and you say, okay, we have some idea of what the spatial correlation functions of these data are, we have some idea what the signal to noise ratio is, and we know where we have data. And if we say, let's say we have a large scale signal, an anomaly of unity, okay, and we plug it into each place we have a data point in a given layer, how much of that large scale signal do we recover? And that's what this map is. You can think of it as a percentage of volume sampled for these various layers. And this is for heat content in any given layer for a single year. All right, so before the International Geophysical Year in the late 50s, we really had sort of pretty low coverage of the global ocean in any given year. That ramps up to over 70% by the IGY. Okay, fair amount of MBT use. Then when shallow XBTs came along from 90 to 450 meters, suddenly we ramp up from about 50% to about 70%, and that's about 1967, right after the XBT came into widespread use. Then during the World Ocean Circulation Experiment in the 90s, we switched over from the shallow XBT mostly to the deep XBT, and now you can see you're getting above about 70% for the upper 700 meters of the ocean. 450 to 700 meters. You can see that deeper than that, you're kind of chugging along at going down to 1,000 meters, which is a place where a lot of people would terminate bottle stations. You're chugging along at about 50% right through the World Ocean Circulation Experiment, and down deeper, chugging along at maybe 30% and to 2,000 meters, and then even deep to get down to the bottom, down at sort of about 10 to 20% per year. All right, so not very good. You can see this little bump up during WOCE, the World Ocean Circulation Experiment, which I'll talk about a little later. And then you can see actually post-WOCE letdown when everyone said, that was a lot of work. We've done it now. We don't have to do it anymore. And people like me were saying, no, we got to keep doing it. And that's what this is. But then Argo has really revolutionized oceanography, and this is the upper half of the ocean volume that we're now sampling at about 90% of the global ocean volume in any given year. Another way of looking at this is just to look at the patterns versus depth in the columns. So we're going from the MBT 0 to 100 meters in the upper part to Argo, say 900 to 1,800 meters down the back versus time. And here red is bad. It's low global coverage, as low as 10%, and blue is good. It's above 90%. Okay, so you can see from the 50s to the 50s and 60s, this is sort of post-IGY. We're getting decent coverage in the northern hemisphere, down to 100 meters, not so good down to 400 meters, and really not very much coverage for a yearly estimate here below that. During the IDOE in 1970s to 89 before WOCE, doing pretty well in the upper 300 or 400 meters with XBTs, okay, but not in the southern hemisphere. And then finally during WOCE, we're actually getting down to below 700 meters with XBTs again, not below about 30 south, not much in the southern hemisphere. But Argo, you can see we're getting blue all the way down to 1,000 meters after about 2004. That's maybe a little premature. It's really, we first get global coverage in about 2005, 2006. So what is Argo? Well, Argo allows us year-round high-quality temperature and salinity data through a fleet of robotic profiling floats. These data are publicly available in near real time, usually within 24 hours of collection. It started in about 2000. You can see here the profiles again in thousands from 2000 through 2015. By 2015, we had 150,000 profiles around the world of data from these floats. It's quite much higher quality than XBT data, much more accurate, and it gives us salinity as well. So it's sort of unprecedented. And here's the most recent position of an Argo float, of all the Argo floats within the last 10 days, there are almost 4,000 of them out as of last week sometime. So global coverage year-round, really much better for mapping CTD data. Here's a typical Argo mission. They used to spend 6 to 12 hours at the surface to transmit data to satellite. They would transmit about 50 to 100 temperature, salinity, and pressure triplets that were collected during their ascent via CERES Argo. So that was about 1 baud, effectively. So it was sort of like a densely sampled bottle cast. Most of these, actually the majority, are now switched over to Iridium rather than CERES Argos. We can now transmit 1,000 temperature and salinity triplets. So basically the same you have from a processed CTD, open ocean CTD cast, 2 decibar resolution, and that takes about 15 minutes. They descend and ascend at about 10 centimeters a second, so it actually takes them about 3 hours to get most of the way to 1,000 decibars. They drift with ocean currents for 9 days, then descend down to 2,000 meters and collect these data on the way up, and they sample. This is a remarkably efficient array. There are over 4,000 of them, and the whole underwater array consumes about 100 watts. So they're powered, the ones that we put out are powered on 12 double D lithium cells, and they can last as long as 6 to 8 years. We have some that have lasted over 10. So that's not the average. The average lifetime we get is about 4, maybe we're getting close to 5 now years. But because other things can kill a float other than running out of batteries, right? But this has really changed things. So if you look at an update now of heat content, and this is going to be published in the annual State of the Climate estimate. I think these curves are all final at this point, although it hasn't gone through review. But what this shows you now is a similar curve for the upper 0 to 700 meters. And I have aligned these curves so that they all agree during this time and then set them to their net zero at baseline. But there are 5 curves here from 5 different institutes, and they're all showing a very similar trend. This one here is the Dominguez et al. Curve, the one that I like for the error bars, but it is a very different method, and I think it's not the best method when you have a lot of data, actually. And so all of these guys there is a little difference here, and I think that's actually because this is an El Nino year, and the Dominguez methodology is sort of sensitive to that. So what am I trying to say here? Well, now we've got tighter error bars on all these. The curves are all showing a very similar trend over this time period. And in fact, we can now do estimates down to 2,000 meters with some reliability. So Argo really got to first global coverage around 2005, and all these estimates from these three groups of heat from 700 to 2,000 meters we're getting annual estimates that are in pretty good agreement. Down deeper than that, we also have an increasing amount of heat down below 2,000 meters, but this is from repeat hydrographic sections, and that's something I'll talk about in the last part of the talk, and we can really only get decadal trends. But even the deepest ocean is gaining heat here. All right, so Argo and ocean energy storage. This is after a little very short comment that we published in Nature Climate Change in 2016. And what we wanted to note here was that now the total trend we can estimate with Argo from 2005 to 2015 as 0.71 plus or minus 0.10 watts. Now, if you remember what the IPCC was doing even back in 2014, we had sort of 0.6 plus or minus 0.4. So Argo has really allowed us to nail this energy storage. 0.61 of this is in the upper ocean. The rest is in the other parts of the climate system. So Argo is really nailing the global energy storage trend, and it's used actually to anchor the CERES energy flux observations. All right, so the long-term trend in CERES, that the energy imbalance is really based on this thermal energy storage, which is mostly Argo. So all the light blue is Argo here. The deep ocean is repeat hydrography, and then these are actually, I just pulled these from the IPCC estimates, so they might be a little small because they're based on a previous time period, and the Earth's warming up more quickly now than it was even at the time of the IPCC. But the other interesting thing is that some interannual variations are just starting to poke their nose up above the error bars, above the trend. And we're going to look at that next. And we'll look at it both with Argo and CERES. So this is when we get to the haiku part. So we'll look at El Nino and ocean warming, CERES and Argo. And as El Nino builds, Pacific warm pool expands, ocean gains more heat. Alternately, you could have something like as El Nino wanes, Pacific warm pool contracts, and ocean gains. It may cool. Actually, the last one, it did cool. That's a big one, though. So El Nino and redistribution of heat, we'll look at CERES and top of the atmosphere energy flux measurements, and then compare CERES and Argo energy storage relation with El Nino, and then just compare that, the energy storage variations and trends to global surface temperature variations and trends. All right, but what I'd like you to actually take away is that the CERES and Argo interannual energy storage anomalies agree. And these are two independent systems, all right? We have satellite measurements at the top of the Earth that are measuring these variations in year to year, and Argo, which is also doing it by energy storage in the upper ocean. And those agree within their error bars, which is a remarkable thing. All right, so if we think a little bit about El Nino and La Niña conditions here, just as sort of a prelude to this second middle section, as we have La Niña or normal conditions, either one, you have strong trade winds along the equator. They tend to pile warm water up in the western Pacific in the warm pool. They drive upwelling through equidivергence on the equator, right? You have flow to the right of the wind in the Ekman layer in the northern hemisphere, to the left of the wind in the southern hemisphere. So you have the thermocline coming up, cold water there in the eastern Pacific. So you have the deep warm pool and a shallow thermocline in the east. Think about what happens during El Nino. The trade winds relax in the west. You even get maybe some mean easterly flow in the western Pacific. The convection all shifts to the east. Clouds actually change around the planet. The big changes in the weather system. But here in the ocean, you've got a shallower thermocline. This warm water spreads out on the surface, and the cold water actually goes deeper again. And so there's a vertical redistribution in the global average as well as a regional change. And you can see that when you look in layers. So what Abigail and I did was to take the time series from Argo, which went from 2004 through mid-2016, and we regressed annual and a semi-annual harmonic, a long-term trend, and then we against the Niño 3.4 index. And this is the regression against the Niño 3.4 index. This is heat content in a couple different layers, 0 to 120 decibars and 120 to 440 decibars. You'll see why we picked those two layers in a little bit. They're basically related to the vertical shift heat. And it's in gigajoules per meter squared, whatever that means. But basically, this is warm during El Nino. The upper layer is warm during El Nino. Warms in the east as that thermocline deepens and the warm pool spreads eastward, and then cools a little bit in the west in the upper 120 decibars, even as the thermocline comes up in the west. And then as you get deeper, you can see the cold water, the warm water. There's still warming here, but there's a lot more cooling over here. And that's because the thermocline has come up. That deep warm pool has actually all shifted over here. All right, so if you look at this in a global average sense, this is what you see. And this is after a nice paper by Remick and Gilson, 2014. It's just updated for the State of the Climate Report in 2017. What this shows is global average temperature anomalies in degrees C here. Red being warm, blue being cold, from 64.5 south to 64.5 north, I think, so near global actually. And you can see 2009-10 was a weak El Nino year. This is a very strong El Nino year. You could see this warming of the surface during El Nino years and actually cooling subsurface in both of these. And here's a La Niña period, another La Niña time period. So there's this vertical redistribution of heat. And then the plot on the right here is just to show that there is also a long-term trend. And so the long-term trend of this, if you just take it and fit a line to these values, you've got a trend of about 0.18 degrees C per decade here over the last decade of surface temperatures around the global ocean. If you don't like that, though, and there's reasons why you might not want to alias El Nino in there, we can also regress, take the Niño 3.4 regression out, and that's what the blue curve is. And so you can see this, this blue curve is a little bit, not the warming trend's not quite so fast. It's not influenced by this, as influenced by this big El Nino because we've taken it out, essentially. But also it's a little more monotonic. But there's a trend that actually continues right down to 2,000 meters of warming over the last decade. And you can see that as in this change from light blue to light yellow in the deeper part of the water column. All right, so that's a way that you can look at the redistribution. I haven't done the vertical integral yet, though. That's a little dicier, but we'll do that in a minute. Well, I haven't showed you the interannual variations, so I guess I've hinted at them. But here's CERES, the satellite top of the atmosphere energy fluxes. This is just 1 day's worth, one hemisphere's worth over 1 day. I just pulled it from the CERES website. What this shows is the outgoing long wave radiation in watts per meter squared, where this is the orange colors are a lot, the lighter colors are less, and then reflected solar radiation. And you can see exactly what you might expect, where it's relatively cloud-free in the subtropics and over the continents, you get a fair amount of re-radiation back. Long wave radiation going out, it's blocked by the clouds. There's probably not, it's colder up here and down here, so there's not going to be so much outgoing long wave. And then the reflected solar, you can see here, again, reflected off the cloud tops, off of the ice sheets, off of some of the more reflective land surfaces. The oceans, where they're cloud-free, are obviously a good absorber of solar radiation, and that's why they're taking up 93% of the excess heat, or one of the reasons why. So these are precise. They're actually, probably give you better coverage, spatial coverage than Argo does, but they require an in situ anchor for accuracy. That's because, again, this is the small difference of two big numbers that get you this. But if we take these, which are in watts per meter squared, and now we take out the seasonal cycle and the trend in CERES, and the trend is really just an Argo-based trend, actually. So if we take out that trend and then time integrate them, we can go from watts per meter squared. We integrate them over the surface area of the Earth. That gets us to watts. We've done an areal integral. Now we do a time integral, and we can get to joules. Okay? So, or zettajoules, which is the heat storage. So if we take the integrated, the time and space integrated CERES measurements, and then compare them to the anomalies the deviations around the long-term trend in heat storage, we get this curve here. So the blue are the CERES. The dark blue is the CERES measurements, and those are monthly. The light blue are the Argo yearly anomalies. Okay, and I daren't go any finer than yearly, unfortunately. The coverage is just not good enough. But these are pretty well correlated. These are correlated about 0.7 or so. And they are also, as you'll note, correlated with the Niño 3.4 index. So that's on the right here, this temperature index. This was done in summer of 2016. We actually only, I think, had CERES data through like February. So that's about where this ends. So we didn't get the fall, but we got the rise, and we got the rise during the 2009-2010 El Nino. These are not well correlated, say the in situ of the satellite prior to about 2005, and that's because Argo wasn't really global back then, and so we didn't yet have a good enough observation system to get at the interannual changes. And And then you'll note that CERES and Niño 3.4 aren't really terribly well correlated before about mid-2002. And there was actually one satellite. That's when the 2 CERES satellites came on board. And I think the correlation noticeably improves after that. So this, I think, is pretty cool. El Niño is modulating both global mean surface temperature and ocean heat storage variations. The CERES and Argo interannual storage anomalies agree. When El Niño is ramping up, the Niño 3.4 index is ramping up, Earth seems to be gaining more energy. And when it's going down, Earth is gaining less, or even giving some back to space, depending on how strong the El Niño is. But it's kind of interesting to compare this to global surface temperature anomalies in El Niño. So here's the 10 years we have for the heat content. You can see that I've reproduced this from an earlier slide. You can see the little interannual variations around the trend here, right? Those are El Niño related, but they're not big perturbations to the trend, right? Whereas if you look at the global mean surface temperature, and this is just from a World Meteorological Organization website, these are now global surface temperature anomalies, global mean surface temperature anomalies for any given year, and they're classified. Red is El Niño, blue is La Niña, yellow is neutral, and volcano, post-volcano years are in brown. When the volcanoes are up, you send a bunch of sulfates up into the stratosphere and reflect solar radiation, so the Earth cools a little bit relative to the long-term trend. But again, you can see this long-term trend, but much bigger swings in the surface temperature. So that's, and this is just a table quantifying that. If you look at the trend for the surface temperature from, say, 1980 to 2016, when we have satellite measurements, you can see that the trend is about 0.0135 degrees C per year. If you look at the correlation around that trend of the Niño 3.4 to the surface temperature, it's about 0.48. So not explaining all the variance, but some of it, at least a little bit, with a response amplitude of about 0.85. So that's actually 6 times the annual rate of increase. So even a 1 degree C Niño 3.4 index is equal to about 6 years of global mean surface temperature trend in terms of its effect on the global mean surface temperature. Whereas if you look at energy storage, the trend is about 11 zetajoules per year over the last decade. The correlation coefficient is actually better. It's 0.72. And this is all from CERES, by the way. This is not from Argo. This is from the monthly CERES data that I'm looking at this. The response amplitude is about 3.4. So that's about 0.3 of a year for one unit index change of Niño 3.4. Of course, the last El Niño was much larger than that. It was up above, up at about 2.5, so considerably larger than a unit response, probably about a 10 zettajoule perturbation, something like that, 8 or 10. So, and that pretty much finishes up the second part. Earth's energy storage and surface temperature are both rising over decades. Both quantities are correlated with El Niño, but the Earth's energy storage trend is steadier than the surface trend. All right, so let's look at the residual. I'm an oceanographer. I love the deep ocean, the abyssal ocean. So talk a little bit about the prospects for observing the half of the global ocean below Argo. That's the next biggest term in the Earth's energy balance that we're still not measuring quite so accurately or extensively. So this is that World Ocean Circulation Experiment, hydrographic program, the WHP, an acronym within an acronym, but WOS hydrographic program. In the 1990s, this gave us an accurate ocean climate baseline. Each of these lines represents a full depth transocean section, sampled usually at about 50 kilometer spacing, 55 kilometer spacing, every degree of latitude. The temperatures are accurate to about 2 millidegrees and salinity to about 3 parts per million. And I should hasten to add that there's a lot of other parameters that are measured that Argo doesn't measure on these cruises. Carbon, oxygen, nutrients, you name it. a huge amount of chlorofluorocarbons, a lot of things that you don't get from the Argo array, but also the deep ocean temperature below the sampling depth of Argo. So this was a huge international effort. It took 10 years to do all these sections. Every decade we're now trying to redo a section, a subset of these sections, and they are chosen so that you have at least one north-south section in each deep ocean basin, and then an east-west section, mostly in the subtropics, and that's where the ocean is transporting the most heat generally and the most carbon dioxide. So those are maximums in transports, in meridional transports. Let's just look at one of these now. And this is a section that's been occupied 3 times. We'll look at the portion from the equator down to about 60 south in the western South Atlantic. So that's what this next slide is. So this shows you observe deep ocean warming in that section. So we're going from the equator down to almost down into the Weddell Gyre here, the northern edge of the Weddell Gyre at 60 south. We're going from the surface to 6,000 meters, 6,000 decibars. And in red are the warming trends or cooling trends in millidegrees C per year, so saturating out at plus or minus 8 millidegrees C per year. And then overlaid on that are the mean temperatures for the 3 sections. And these were taken in 1989, 2005, and 2014. And they're contoured from 4 degrees C at 0.2 degrees C intervals down to below 0 here. All this stuff is below 0 here. This is all below 1. And there are a couple things I'd like you to draw your attention to. First of all, there's some eddy striations here. You can see these alternating blue and red stuff. This is, even when you're averaging over 3 sections, you're still getting some mesoscale eddy noise. The other thing I'd like you to draw your attention to is this strong gradient in the contours, the black contours here. That is the boundary between Antarctic bottom water, which is flowing north in the Brazil basin here, so up from the Weddell. Oops, let's see. I've lost the pointer. Okay, so up from the Weddell Sea this way, and then up here you've got North Atlantic deep water. And that is sort of above 2 degrees C up to about 4 degrees C. You can see the Antarctic bottom water is really warming pretty dramatically here and steadily at a rate of about 3 to 5 milldegrees C per year. That is actually a rate that is equivalent to somewhere around a third of the surface global mean surface temperature warming rate. So it's pretty strong. And it's also over, a kilometer of ocean, and you can store a fair amount of heat with that pattern of warming. And then the other thing is the North Atlantic deep water, at least in this section, is not changing very much. So it's really this. There's a Southern Ocean signal. This area here, all this cold water's warming, and this water's warming. And when we looked, Sarah Perkey, my student, and I looked at this. We saw. We got this map when we looked at all the repeat sections, and we just looked below 4 kilometers. So we sort of looked to cut in at this Antarctic bottom water signal here. You can see a strong pattern of warming around the Southern Ocean, and then it's warming a little bit less as you go further north, and a little bit less here. Even this basin, though, is actually warming all the way up to 50 north, to 47 north here, this section here. Fukazawa and Howard Freeland noticed this back in 1999 when they first reoccupied this section. Here, these are saturating out at 5 millidegrees C per year, plus and minus, and the little stippled areas are not statistically significantly different from 0 at 95% confidence. So the errors are actually overwhelming. The uncertainties are overwhelming the trend here, but all the unstippled areas are. So all the cooling areas, actually, except for this basin here, are not statistically significantly different from 0, but most of the basins where you see warming are. And this ends up to be about somewhere around 15% of the global heat gain over the last couple decades is going into the deep ocean, Unfortunately, we don't know whether it's 5% or 25%. Bob looks like he's got a question.
So in the southern Atlantic,
Yeah.
there's a blue part on one side and a red part on the other side. Could there be a little bit of a gyro wobble in there that could be showing up as a...
It's possible. The other thing about this basin is we've got only a couple short sections, and it's a really energetic basin. But yeah, it is possible. If you think about what would be happening, yeah, this is a little. Now, I think this is actually related to a slowdown in the Antarctic bottom water, not just a warming. And if you think about the shear in the southern hemisphere, if you've got a bottom intensified flow, take a section, say, across here, the isotherms are going to be slanting up at the western boundary and down at the east. You could imagine a tilt like that that went with less northward flow, but that's maybe pushing it a little bit. But anyways, so are we... This pattern actually also is interesting because it looks a fair amount like high-resolution climate models. So this is from a paper by Bryan et al. It shows ocean warming in the decade or so after a CO2 doubling experiment is taken to term. On the left, we have a low-resolution model. Now we're going from Antarctica up to 30 south, and again going down to the ocean floor, at least in the models. So this is I think a 1 degree model, and this is a 1/10 of a degree model. And the 1 degree model forms Antarctic bottom water mostly by open ocean convection, which is not the way it's formed in the modern ocean for most part. The 1/4 degree model forms it by cooling on the shelves, and actually probably resolves that process a little more realistically. And that model, you've got, again, this warming throughout the water column in the Southern Ocean, and then a warming spreading north. So are we seeing this in the models? Possibly. Delving in a little bit more into the models, just to show you that the deep ocean is probably important in diagnosing climate change. This is from the IPCC 2013. Again, this is a whole mix of models. Most of them are probably low resolution, but you can see that this is an average, a 2-decade average centered on 2090 minus a 2-decade average centered on 1995. The changes in the ocean temperature, and you've got this warming all the way to the bottom again in the southern hemisphere, cooling actually in the northern hemisphere. But this one is actually kind of, to my mind, at least as interesting, and this is from a paper by Bowe et al. In 2009. It's a little bit hard to explain, but this is basically the correlation coefficient between ocean temperatures now in a model and projected future warming. So where ocean temperatures are high in a model, anomalously high relative to the model averages, you get more warming, future atmospheric warming, and where they're cool, you also get more future ocean atmospheric warming. So actually, this deep stratification and the Southern Ocean conditions are actually important.